Hi, in this video I will give an update on initial implementation of memory management function of RISC-V RV32IC I have. Like my other updates, a short video will be given at the end of this update. There are three items I will mention regarding memory management here: memory paging, TLB aka translation local site buffer, and memory protection. To make the hardware implementation simpler, a good portion of the operation is assumed to be done in software, which I will explain later. The demo I will give relates more to the first two items. In terms of memory protection, the hardware is available to support generation of protection fault. The rest is assumed to take place in sort of system software, which will not be covered in this simple demo. This is the system we have before, and we will make room for this new implementation. In addition to the new implementation, I also reduced the system clock to 25 MHz. Actually, I already had some timing issues with cache eviction the last time, but I used some logic to mask the problem. Now it's getting worse, so I just decided to lower the clock rate. Starting with paging, when a 32-bit virtual address is generated by a RISC-V processor, according to the documentation, each memory page size is 4 kilobytes. This takes 12 bits from the memory address to index a byte location inside of one page. The rest of the address bits, 20 bits, serves as the virtual page number from the processor. When paging is enabled, the 22-bit page number can be mapped to any of a 4 kilobyte physical page by mapping tables. For a 32-bit processor, a 20-bit virtual page number can be mapped to 22 physical page number. A CSR register SATP is implemented to support the paging function. The highest bit, bit 31 of this CSR register, is the paging enable bit. When paging is disabled by storing a 0 in bit 31, then it is just a straight path through from the virtual page address to physical page address. And as the physical page number is 2 bits more than virtual page number, the highest 2 bits will be filled with zeros in this case. The physical address mapping, or physical page translation, is done by a two-level page table scheme to reduce the required table size, which I will briefly explain here. Let's start with a virtual address from the processor and a 22-bit page number stored in SATP CSR register. The physical page number in SATP CSR register points to the base of the first level of page table in physical memory. The highest 10 bits of the virtual address then serves as an index inside the first level of page table to get a physical page entry, PPE, from the physical memory. The physical page number in the first page number entry then points to the base of the second level page table, level 0. The next 10 bits from the virtual address then index into the second physical page entry from second level page table. The physical page number in the second physical page entry combined with remaining 12-bit page offset from virtual address forms the final translated physical address. This completes the virtual address translation. When there is no match in the existing page table, then a page fault trap is generated. During the process of virtual address translation, however, various protection bits must be observed, and protection fault will be generated if rules are violated. If all the steps needed to be done for every memory access, it can be pretty slow. So this is where TLB comes in. TLB is a cache memory for page table described previously. A virtual address from the processor is compared with several page entries to speed up the translation process. In this experiment, an 8-entry fully associative cache is implemented for the TLB block. It's not very big in size, but it's what I can afford with what's remaining with the FPGA resource. A bigger cache size and/or an additional n-way set associative cache can be used in parallel with the supposedly smaller and faster fully associative cache. And the timing penalty that bigger cache and set associative cache, like my previous implementation, can be slow. But it may be still faster than taking a TLB miss and page fault trap. This page is more for my own note. If we can always have memory cache on, then maybe we can use n-way set associative cache scheme even for regular TLB, etc., etc. Now, for the demo plan, I will reuse the rotating cube program from previous project update. The idea is for the program to draw either on the left or right side of the screen. I will have 2 copies of the same program loaded to 2 different locations. A periodic timer interrupt will alternatingly activate one of the program with proper page mapping. The final result would be I have 2 copies of exact same program running at different locations in the memory space, but thinking they both occupy the same space because of memory mapping. On this page, it is additional constraints and page mapping for this demo. Now, here's the simple video demo. The graphics is not very smooth, partly because the interrupt routine I wrote is not very efficient, that there is a short period of time periodically that both cubes paused. Okay, that's all I have for this update. Until my next project update, thanks for watching.